Hello, this is Thomas from investmentexcel.com. Welcome to this session on the Black-Derman-Toy model from 1990. This model is a calibrating model or a no-arbitrage free model. The calibration means that the stochastic interest rate projections in the model, they are contingent on the current prices of the zero coupon structure and on the volatility structure. So the interest rates in the future generated from the model, they are calibrated or calculated backwards in order to price today's term structure of zero coupon bonds and the term structure of volatility. This particular feature makes it very appealing in the financial market. This video and the Excel workbook are both available for download on Investment Excel or on spotafile.com. Let's take a look into the model and keep focus on how the model is applied and how it works. Originally, the theory behind the model was a stochastic differential equation with a time-dependent drift component and a time-dependent diffusion component or volatility component. So exactly this time dependency makes the model a no-arbitrage model, as it is flexible in terms of generating the stochastic interest rates to fit the current prices of zero coupon bonds and volatility. Both the distribution of short rays is very complicated, but luckily there is a discrete counterpart that we can apply instead when simulating the stochastic rates. I will show it here in a tree with 10 maturities and 10 states, and I will also assume that volatility, the sigma in this formula, is constant, and it will be constant at a level of 10%. But it could have been flexible with time. We could fit the model anyway. This is just for the sake of simplicity, and actually in practice this is also a very normal feature. So first we have to observe the current term structure of yields, and I have it here, starting from 2% on a 1-year maturity to 10-year. And this is all the input we need right now, along with the 10% in volatility. With this input we can start building the interest rate tree. Just with this parameter here as sigma, and then as drift for every time, the A, I just arbitrarily choose some values. Oh, not here. That's given. It's a binomial model, so if we start here, there is an up and down. If we go to the upper here, there is an up and a down, and so on. Also, the model is a risk neutral model, so there's a 50% chance of going either up or down. When we have this tree, we can either start to calculate each zero coupon bond with all maturities based on this, and then move or calculate backwards and see if it fits the right prices. A smarter way of doing it is by using what is called a forward induction method, where we can calculate on each maturity state prices that we can sum, and which gives us the exact present value model price on that maturity. So for instance, right now, with the arbitrarily chosen future stochastic rates, we have an observed price of a 10-year zero of 0.6595, and the model is 05653. So the whole idea right now in the calibration is to make these exactly the same on each of the maturities, and we do that with a simple quadratic optimization method. So we take the difference and square them in order to avoid any netting. So just as a normal quadratic optimization routine. And here we have the sum, which we have to minimize. And the minimization is a trial and error, and I could start again arbitrarily typing in different rates, and perhaps in 500 years I will find the lowest value. I could use Excel, and I choose to do that just by calibrating the state prices. So this was a good start. It's because I have another sheet open, so I will just do it manually. So the idea is to set the objective, which is the RSE, and I will minimize it by changing the values on the green line, except for the first one, which is fixed. We know the current yield, so we don't have to change that. And I'll try to solve. And it's calibrated. See here 0. There's probably some digits out there somewhere. So here's the tree, and the tree is now governed by this process, but it's constrained by the fact that pricing a zero coupon bond on this tree should give the price today observed. So let's just test that idea by taking, for instance, a 5-year zero coupon bond. It has 0 in coupon, and the principal I will set to 1. I will just go down and show how the cash flow looks. Obviously no cash flow from 6 and onwards, but on year 5 we expect in all scenarios, in all states, to receive 1, and on all other maturities, due to its zeroness, there will be no cash flow. And we can calculate backwards as we normally do. So starting on the first note by discounting the expected value of the upper state and the lower state, and the expected value is under the Q measure, under the risk neutral measure, so it's a 50% chance of going up and down. So obviously it's 1 divided by 1 plus discount rate for this particular note, and it's this one. And so we do, and the pricing here should be the price of a 5-year zero coupon bond today. And how can I see that? I can go, which way should we go? I'll just go the other way here and take the 5-year yield. The 5-year yield, and raise it to the power of maturity and see if it gives us the one that I was looking for. And here we have it, and the one that I priced was here, and perhaps it's the same. It should be. It should be 6 decimals. Yes, it's the same. So we have priced correctly the tree, and it can now be used for pricing any other interest rate related product. It could be a coupon bond, it could be it could be a mortgage bond, it could be a credit bond, it could be a derivative, could be a derivative based, just say on what is on year 8 in this scenario. It could be path dependent derivatives, where you have to take, say, the average of a certain path. So this is the idea, that we now have a calibrated tree of interest rates, and we can use all those interest rates on particular times. It doesn't have to be with 1 year. It could be with quarter or semi-annual steps. And yeah, use the volatility structure on each time. So even though the volatility is constant through time, it's not constant on time. This is still given by the state, the up and down. There has to be a force to drive it up and down, and that's the volatility. I'll just price another product. Could be a 10-year coupon bond, 5, principal 100, and this one has a price of 107. And say that we know that we have this structure of a bond, of a bullet bond, and I would actually like to have a risk premium over the zero coupon yield curve, represented here by the set spread. I would like to have 2% extra due to credit risk or liquidity risk versus credit and liquidity risk on a government bond implicit in the zero coupon structure. Then the price would be 92. Alright, I think that sums up. I should perhaps just say how it works with the set spread. The set spread is a constant spread that is put on all zero coupon bond yields, and for the tree it means that this constant spread has to be added on all nodes, each and every stochastic rate in the grid or in the lattice. Say for instance I put 2% on, and you will see it moves upwards in parallel with 2% all the way, and the discounting will take place down here. Obviously with this one you can also test sensitivity, duration measures, and so on. Anyway, this grid is easily implementable on very long maturities as well, 30-year bonds with many time steps. It's just copying the sheets. All formulas are built in Excel and very intuitive. So yes, thank you for listening. Goodbye.